Welcome. Tonight, our journey takes us beneath the waking world, down past the bright, thin skin of the sea, into the long, quiet basalt floor of the Pacific. It is a place that exists right now on our own planet, yet remains almost entirely unseen. We are going to descend, slowly, into the dark. Welcome to Midnight Volumes. Tonight, we sit with the slow furnace beneath the Pacific. Let the lights of the day finish their business without you. Loosen the small grip the surface has on you. We are going down. Imagine, first, a calm sea. Not a storm, not waves, only the long, slow breath of the ocean, rising and falling against the curve of the earth. The boat that brought you here has gone quiet. You step over its edge and slip below, into water that is, at first, warm and lit and familiar. Sunlight scatters above you in shifting blue panels. The world you came from is still close enough to touch, if you stretched. Then you sink a little further. The blue darkens, the warmth lifts off your skin and is replaced by a deeper, cleaner cold. Light still reaches you, but it is thinner now, and bluer, like light strained through old glass. You are leaving the part of the ocean that knows the sun. This is called the epipelagic zone, the sunlit upper layer. It is everything you have ever swum in. It is everything most of the planet's life has ever seen. And it is, in the great vertical column of the sea, a thin film, a skin. A few hundred meters of brightness above thousands of meters of long, quiet dark. Keep sinking. At about 200 meters, the last useful colors fall away. Red is the first to go, then orange, then yellow. By 300 meters, only a faint blue-green twilight remains, and even that is more a memory of light than the thing itself. You have entered the twilight zone, the mesopelagic. The water here is cold and dense and quiet. Things still live here, things with large eyes and small lights of their own, but they prefer the dark, and they will not come close. They flicker past at the edges of your awareness, soft, small lamps switching themselves on and off, and then they are gone. If you were a sound, you would carry far down here. The deep ocean is a famous conductor of sound, and a single faint click can travel for hundreds of kilometers across this quiet. But you are not a sound. You are only a quiet thing moving down through a quiet medium, and nothing notices. Keep sinking. At 1,000 meters, the last trace of surface light is gone. The water around you is not dim. It is not low light. It is, in a real and physical sense, completely black. This is the bathypelagic, the deep midnight. It is also where the ocean stops being a place anyone walks through. It is a place that simply is, pressure and salt and slow currents and time. No storm reaches this far down, no wind, no season. The temperature drifts only by a degree or so, and very slowly. The water has been at near freezing for thousands of years. It will be at near freezing for thousands more. If you brought a candle down here, it would be the only flame in something like 100 million cubic kilometers of water. And then it would go out, because there is no oxygen to spare for a flame in a place like this. There is, however, life. There is always life. It moves slowly, and it does not glow much, and it does not get in your way, but it is here. We will meet some of it later, when we sit a while in the gardens. Above you, more than a kilometer of black water now stands between you and the sun. Above that, still more water. Above that, the thin skin of waves. Above that, the air. Above that, the sky and the long fall of stars. You are far down, and we are not yet anywhere near where we are going. If you enjoy these gentle journeys, I invite you to like, subscribe, or share a thought below. It helps others find their way here, too. Keep sinking. By 2,000 meters, the water has been at near freezing temperatures for a long time. It moves so slowly that the same parcel of water can take centuries to cross an ocean basin. The pressure on every surface of you is enormous. Many tens of atmospheres pressing in from every direction at once. But you are weightless in it, neutral, suspended. You are not falling. You are simply held. At about 2,600 meters, the average depth of a mid-ocean ridge crest, you begin to sense, rather than see, the bottom. The water has a different quality. There is a faint shape below you, a long, low ridge running away in both directions, farther than you can follow. The ridge rises about 2,000 meters above the deepest parts of the ocean basin, a slow mountain range that no human eye has ever seen in full. The deepest sea floor goes another 4,000 meters below it. Most of the world's mountains are down here. Most of the world's volcanoes are down here. And this is the part most people never think about. The numbers are quiet, but they are large. The submarine volcanoes alone, the ones at the mid-ocean ridges, are estimated to account for about 75% of all the magma erupted on this planet. Not most of it, the vast majority of it. Almost every cubic kilometer of new crust that the Earth has made in the past 100 million years has been made in the dark, underwater, with no one to watch. The total number of submarine volcanoes is estimated to exceed 1 million. Of those, roughly 75,000 are tall enough to rise more than a kilometer above the seabed. They are taller than most subaerial mountains. They are draped in deep water. They are almost entirely unmapped. Of this million plus, only 119 are known to have erupted in the last 11,700 years. The rest are silent, or sleeping, or erupting so quietly and so deep that no one is listening. The Earth's loudest geological process is the one we cannot hear. Let that settle for a moment. There is a small mountain range running through every ocean on Earth, and it is making, right now, the planet you live on. The continents move because of it. The water you swim in is partly salted by it. The minerals in your blood, the iron in the rust on an old gate, the copper in the wire of your bedroom lamp, Many of those atoms came up out of vents like the ones we are about to visit.
It is, in other words, not a separate world down here. It is the workshop of the one you know, and it has been at work in this exact way for billions of years, long before there were continents in their current shape, long before there were forests, long before there was any creature soft enough to dream. This slow furnace was already running. The rocks of every coastline you have ever walked on, every stone in every wall of every old city, every grain of sand, traces some ancestry back through this slow underwater machinery. The hills are downstream of the dark. It is easy to forget. We see the world that the sun lights up, and we assume that is where the work is done. But the deep work, the slow, patient, planet-scale work, is done down here, in long, quiet darkness, and no one watches. There is no horizon. There is no orientation. There is no sound, except occasionally a soft tick from somewhere far away, a vibration, a faint click of rock, a small adjustment of the planet. Your eyes are still open. They cannot help you. They are not the tool you need anymore. The water here has a temperature of about 2 degrees Celsius. It has been about 2 degrees Celsius for a very long time. It will be about 2 degrees Celsius for a very long time after. The deep ocean is the slowest weather system on the planet. Nothing rushes. Everything that happens here happens at the pace of stone. The Pacific Plate, the largest tectonic plate on Earth, at roughly 103 million square kilometers, lies beneath you and around you, drifting almost imperceptibly. A few centimeters a year, about the rate your fingernail grows. That is the speed at which the floor of the planet is rearranged. That is the speed at which mountains are born and trenches are eaten. We move faster in our small upper world than the planet does in its largest one. The seafloor below you is older than nearly everything we are about to see, and yet it too will eventually be gone, fed into a trench somewhere west of here, returned to the mantle, melted back into rock. We are going to descend a little further, and then we are going to begin walking. Ahead of us, off to the south, there is a long, low spine of submarine mountain, a slow ridge, mostly basalt, running thousands of kilometers beneath the surface of the eastern Pacific. It is where the planet manufactures fresh ocean floor. We will start there. From the rise, we will follow a trail of long-extinct and barely living volcanoes northwest across the Pacific, the slow track of a single deep hotspot, until we come to the youngest of all of them, still hidden underwater off the coast of Hawaii. From there, we will turn east again, to the chimney gardens of Endeavour, where superheated water spills out of the ocean floor at temperatures that should not be possible at all. We will sit a while among the tube worm gardens that drink that water and live on it without sunlight. Then we will drift west to the long, curved trench arcs of Mariana and Kamaʻehuakanaloa, where the floor of the ocean folds back into the planet and burns again. And finally, we will rest in the cycle itself, the slow inhale and exhale of a planet that has been doing this quietly
for billions of years. There is no war between fire and ice down here, only their slow, hushed meeting in the dark. This is not a thrill ride. You will not be startled. You will not be asked to look at anything terrible. The deep ocean does not put on shows. It works at its own slow pace, in its own slow quiet. The way the world has worked since long before there were eyes to watch it. Close your eyes, if they are not already closed. The dark down here will not change whether they are open or shut. The water is the same either way. We are about to follow the long spine of the rise. The long spine of the rise begins, if any one place can be called the beginning, somewhere off the coast of Southern California. From the Gulf of California, in the warm, dim basin of the Salton Sea, a slow seam in the floor of the ocean runs south, and then south, and then south again, all the way down to a junction near 55 degrees south latitude, where it bends west toward Antarctica. It is the East Pacific Rise. It is 2,000 miles off the coast of South America for most of its length. It is, in a quiet way, one of the largest single structures on our planet, and almost no one alive has ever seen it with their own eyes. Move with it for a moment. The rise itself is not a sharp ridge. It is not a knife-edge cliff. It is a slow, gentle swell of the seafloor, rising about 1,800 to 2,700 meters above the surrounding plain. If you could drain the water away, it would look from a distance like a long, shallow wave of stone, 2,000 kilometers wide at its base, running away in both directions, farther than your eye could follow. From close up, it would look like a softly pillowed field of basalt, with low ridges and small fissures and dark-cooled lobes, and almost nothing else. This is where the sea floor is made. Two tectonic plates meet along the spine of the rise. To the west, the enormous Pacific Plate, the largest tectonic plate on Earth, covering about 103 million square kilometers of seabed. To the east, in sections, the smaller plates, the North American, the Rivera, the Cocos, the Nazca, and far south, the Antarctic. The rise is the seam where they pull apart. And as they pull apart, something has to fill the gap. So magma rises, very slowly, from a shallow chamber a few kilometers below the sea floor and reaches the cracked seam and cools. New basalt, new crust, a fresh, narrow strip of the planet added to the world. It does not happen all at once. It does not happen in a flash. It happens at the pace at which a fingernail grows. In its faster southern stretches, the East Pacific Rise spreads apart at about 79 millimeters per year. Not 79 meters, not 79 kilometers, 79 millimeters, give or take a few. This is among the fastest spreading divergent boundaries on Earth, and even so, it is invisible. If you sat on the sea floor at the rise and watched, you would not see anything happen in your lifetime. You would not see anything happen in the lifetimes of all your ancestors put together. And yet, given enough time, this slow motion has built and rebuilt the entire floor of the Pacific Ocean. Let that arithmetic sit for a moment. Roughly 8 centimeters a year, about the width of 3 fingers. Multiply by 1,000,000 years. That is 80 kilometers of new ocean floor. Multiply by 100 million years. That is the width of much of the Pacific itself. The rise has been at work in one form or another for far longer than that. The ocean basins we know are entirely temporary. They are pushed open by the rises, and they are dragged shut, eventually, by the trenches on their far sides. Nothing in the sea floor lasts. Everything is on its way somewhere. Most of the work the planet does, it does here, or in places like this. The mid-ocean ridges, taken together, are estimated to account for about 75% of all the magma that erupts on Earth. That is an astonishing share. The volcanoes you have heard of, Vesuvius, Krakatoa, Mount St. Helens, Etna, make up part of the visible remainder. The vast majority of the planet's actual volcanic output happens silently, underwater, at ridges like this one. We do not hear it, we do not see it, we simply have a planet because of it. A quick survey of submarine volcanoes makes the point clearer. There are estimated to be over 1 million of them. Of those, roughly 75,000 are tall enough to rise more than 1 kilometer above the seabed. That alone is a number worth pausing for. 75,000 mountains drowned. Most of them taller than most of the mountains anyone has ever climbed. Most of them never named. Most of them never seen. Only 119 of all these submarine volcanoes are known to have erupted in the last 11,700 years. The rest are sleeping, or they are erupting at depths and rates we have no way to detect. The Earth's loudest geological process is a process we cannot hear. Move a little along the rise now. Sit, if you can, on the basalt itself. There is almost no sediment here. The crust at the ridge crest is new, geologically brand new. There has not been time for the slow snow of dead plankton and clay to settle on it. So the floor is dark and clean, with a faint glassy sheen where the lava cooled fastest against the cold seawater. The basalt has a particular shape. It looks like a field of stone pillows, fat and rounded and stacked, each one a few feet across. This is pillow lava, the characteristic form of basalt that erupts underwater. The pressure of the deep water clamps the outside of each lava blob into a thin glass skin, holding it in shape while the inside slowly cools. New pillows ooze out between the old ones. The whole field looks soft, even though it is harder than concrete. It looks, in the right light, almost organic, like the planet itself is breathing. There are cracks in the basalt, long, thin fissures, parallel to the ridge axis, running away in both directions. Seawater seeps down into them, sometimes for kilometers, drawn into the hot rock beneath. Down there, in the rock, it is heated and pressurized and chemically transformed. It dissolves metals from the basalt. It loses some of its sulfate and gains hydrogen sulfide. It becomes something that the surface ocean would not recognize. And then, Somewhere along the ridge, it finds a way back up and erupts out as a hot, mineral-rich plume into the cold dark above. We will visit such a plume later at Endeavour, but its source begins here, in the cracks of the basalt at the rise. There are very few creatures here. The new basalt is too fresh, too poor in food. But occasionally, a small white shrimp drifts past, looking for the warmer water that signals a vent. Occasionally, a faint, pale tube worm clings to a crevice, waiting for the sulfur breath of the planet to come back. They are scouts. They are the leading edge of the strange, long-lived gardens we are going to visit further on.
Look out! West, along the floor of the Pacific Plate.
For the entire stretch of the rise, the plate to your west is older than the plate to your east. The plate to your east, younger, sometimes only hours or days old, is being added to right here, under you. The plate to your west has been drifting north and west for a long time. Its oldest parts are 80, 90, 100 million years old. Its very oldest parts are nearer 180. Those parts are very far from here. Those parts are already most of the way to the trenches of the Western Pacific, where we will go later. The sea floor is, at any given moment, a vast, slow conveyor belt, and the East Pacific Rise is one end of that belt. This is the simplest way to think of it. The rise makes the floor. The trenches take it away. In between is the entire Pacific Ocean and everything that lives in it. It is hard to feel the scale of this without slowing down. Imagine, for a moment, a single grain of black basalt sand on the ridge below you. It is the size of a poppy seed. It was new yesterday, cooled out of the magma chamber 1,000 meters below, broken loose from a pillow, drifted into a crack. The plate carrying it is heading west at roughly the speed of fingernail growth. That grain of sand, if you could mark it and follow it, will take perhaps 100 million years to reach the far side of the Pacific. By then, it will be buried under a kilometer of sediment, or it will be at the lip of a trench somewhere west of Tonga, about to fall into the mantle and be erased. This is the timetable on which the planet operates here. Nothing happens quickly, but everything happens. The world is not still, it is only slow. Now let the rise fall behind us. We are going to follow a different track. There is a place out in the open Pacific, far from any ridge or any plate boundary, where a single deep heat source has been quietly pushing volcanoes up through the seafloor for at least 80 million years. The plate slides over the heat source. The heat source stays where it is. So the volcanoes form, drift away, go extinct, sink, and a new one rises in their place. A trail of cones across the ocean. The longest and most studied such trail on the planet runs across the North Pacific, from Kamchatka in the northwest all the way down to the island of Hawaii. We are going to follow the trail of the Hotspot. To follow the trail of the Hotspot, we first have to understand the idea behind it. Once you see it, you can never quite unsee it. The world becomes, in a small way, more legible. In the year 1963, a Canadian geologist named John Tuzo Wilson proposed something quietly radical. He suggested that the long chain of volcanoes running across the North Pacific, the islands of Hawaii at one end, the long line of underwater seamounts stretching all the way to the trenches of Kamchatka at the other, was not a chain of separate volcanoes built by separate causes. It was the trail of a single thing, a fixed source of deep heat, somewhere far down in the mantle, that had been melting the underside of the Pacific Plate for at least 80 million years. The plate, drifting slowly northwest, slid over the heat source like a sheet of paper slid over a hot coal. Each new volcano was a fresh scorch mark. As the paper moved, the old scorch mark cooled, and a new one appeared just behind it. A trail. This is the idea of a hotspot. It is not the only explanation that has been offered for Hawaii, and the deeper details are still under quiet academic debate. But in the simplest form, it works. It explains the trail. It explains the ages. It explains why the volcanoes get older the further north and west you go. It explains, in the end, why Hawaii is where it is, and why it is moving. The Hawaiian Emperor chain is the trail itself. It is a mostly undersea mountain range. Above water, it makes up the Hawaiian Islands, a small, bright archipelago in the middle of the Pacific. Below water, it stretches about 6,200 kilometers to the northwest, all the way to the Aleutian Trench off the Kamchatka Peninsula. Along that distance, there are more than 80 identified undersea volcanoes. Almost none of them rise high enough to break the surface anymore. Most of them are gyo, flat-topped extinct volcanoes whose summits were once islands, eroded down to wave level, and then slowly sunk as the plate they ride on cooled and dropped beneath them. The islands of Hawaii are the youngest part of the chain. The island of Hawaii itself, the Big Island, is less than 500,000 years old at its youngest volcanoes. The other Hawaiian islands range up to about 5 million years old. Then, further northwest, the Leeward Isles, the northwestern Hawaiian Islands, are between 7 and 28 million years old. Beyond them, the Emperor seamounts, the oldest and most heavily eroded part of the chain, are between 39 and 85 million years old. The oldest confirmed age is about 81 million years, for a deep-water seamount called Detroit, near the northern end of the trail. The seamount just north of Detroit, called Meiji, is probably older still. Let that arithmetic sit. 81 million years. The same heat source, the same direction, the same plate carrying away each freshly built island and lowering it slowly back into the dark. There is a kink in the trail. About halfway along its length, the line of volcanoes bends. The bend is sharp, about 120 degrees. Southeast of the bend, the trail runs roughly along the line of Hawaii. Northwest of the bend, it veers almost suddenly toward the north. For a long time, the standard explanation for the kink was that the Pacific Plate itself had shifted direction around 47 million years ago, swinging from a more northern path to a more northwesterly one. More recent work suggests the hotspot itself may also have moved a little, that the trail records not only the drift of the plate, but also the slow motion of the deep heat source beneath it. The bend is, in either case, one of the strangest readable features on the entire planet. It is a corner in the floor of the ocean. A corner left behind by something that happened in the mantle when our oldest ancestors were still small early primates in the trees of an unfamiliar world. When the Pacific Plate carries a Hawaiian volcano away from the hotspot, the volcano stops being fed. The magma below it stops. The eruption history ends. The island, which used to be supplied with new lava from below, is now just a cooling pile of stone. Wind and rain and the sea begin to eat at it. The whole island, very slowly, also begins to sink, because the plate it sits on cools as it drifts away from the rise, and a cooling plate becomes denser, and a denser plate rides lower in the mantle. Over millions of years, the island erodes down to a low rim, then to a reef, then to an atoll, then to a flat-topped seamount with no land at all. The northwestern Hawaiian Islands are at various stages of this process. The Emperor seamounts are at the end of it. Detroit's seamount, the oldest confirmed cone in the trail, has not seen the open air for tens of millions of years. The volcano that built it is gone. The mountain is still there, drowned, slowly creeping northwest at the same pace as the plate. Now turn south, back along the trail, past the Leeward Isles, past Kauai, Oahu, Maui, to the youngest, easternmost, currently active island, the Big Island of Hawaii. The Big Island is built of 5 volcanoes: Mauna Kea, Mauna Loa, Hualalai, Haleakala, and Kilauea. They are mostly the ones above water, but there is a 6th in the family that does not yet have a name on any map most people will look at. It is below water. It is the newest. It is the next. It is called Kamaʻehuakanaloa. For most of the last 100 years, English language maps called this volcano Lo'ihi, a Hawaiian word that simply means long, describing the elongated shape of its underwater ridge. In the year 2021, the Hawaii Board on Geographic Names formally adopted the older Hawaiian name found in 19th century chants, Kamaʻehuakanaloa, meaning glowing child of Kanaloa, the god of the ocean. The United States Geological Survey adopted the new name too. The map was, in this small, quiet way, made more honest. Kamaʻehuakanaloa is an active submarine volcano about 35 kilometers off the southeast coast of the island of Hawaii. The summit of the seamount is about 975 meters below the surface of the sea, close enough that on the clearest day, a deep diver might just reach it. The volcano itself, from the summit down to the sea floor, stands more than 3,000 meters tall. From base to summit, it is taller than Mount St. Helens was before its catastrophic eruption in 1980. And almost no one knows it is there. It is, depending on how you count, the only Hawaiian volcano currently in what geologists call the pre-shield stage. It is still being built up from the sea floor, with steep flanks and a small summit,
and alkali basalt lavas characteristic of a young hotspot volcano. Continued volcanism is expected, slowly, to grow it into an island. Estimates put the date of its surfacing somewhere between 10,000 and 100,000 years from now. It is, in the long view, the next Hawaiʻi.
Kamaʻehuakanaloa began forming around 400,000 years ago. At the rate Hawaiian volcanoes drift northwest with the Pacific Plate, about 10 centimeters a year, the seamount was once about 40 kilometers southeast of its current location, when its first lava pillows began to cool. That distance, 40 kilometers, took it 400,000 years to cover. It will take it longer still to reach the surface. The clock is geological, not human. The Big Island will not see Kamaʻehuakanaloa emerge in any of our lifetimes, nor in the lifetimes of anyone whose lineage we can imagine.
In the summer of 1996, however, the volcano made itself briefly known. A swarm of 4,070 earthquakes was recorded at Kamaʻehuakanaloa over a few months. At the time, the most energetic earthquake swarm in Hawaii's recorded history. The summit changed shape. A hydrothermal field near the top, called Pele's Vents, collapsed entirely into a pit. The new depression, now called Pele's Pit, is about 200 meters deep at its walls. The volcano, which had been quietly building itself up for tens of thousands of years, in one summer suddenly carved away a piece of its own top. It has been quiet since then, in the way an animal is quiet between breaths. Around the volcano's many hydrothermal vents, in the dim water at 975 meters, a diverse microbial community has made its home. The water there is warm, mineral-rich, slightly acidic. The bacteria that live in those vents include some of the most thermally tolerant on Earth. They are the leading edge of the kind of community we are about to visit, at a quite different volcano, in much colder, deeper water, far to the northeast. Sit for a moment on the southern flank of Kamaʻehuakanaloa, in your imagination. The water is dark and cold, but warmer than it should be for this depth. The basalt under you is fresh, glassy, lobed. The plate beneath the basalt is creeping northwest by 10 centimeters a year, carrying you with it. Below you, somewhere, the heat source of the entire Hawaiian chain is still pushing magma up toward the surface, very slowly. Above you, almost a kilometer of dark water, then surface, then air, then a sky which today is full of clouds over the Big Island. You are the leading edge of the next Hawaiʻi. You are also simply a quiet lava pile far from anywhere. We could stay here longer, but there is another place to visit, far to the northeast, where the floor of the Pacific does something different. It does not just build a mountain quietly out of basalt. It breathes. It exhales superheated mineral water through chimneys that grow as fast as a person's height in a season. It is the next stop. Where the plate is born, it also breathes. Listen. Now, for the chimneys at Endeavour.
Where the plate is born, it also breathes. The seafloor is not only built at the ridges, it is also opened. Tiny cracks, long, thin fissures, wide circulating systems where cold seawater is pulled down into the hot crust, transformed beyond recognition, and then released back into the sea, much hotter, much darker, much heavier with dissolved metal. That released water is the breath of the planet. In the most literal sense, we can use those words. To listen for that breath, we move northeast. We leave the East Pacific rise behind. We follow the coast of North America, up past California, past Oregon, past Washington, and a little further. Off the western shore of Vancouver Island, in waters that are Canadian by jurisdiction, the floor of the Pacific is broken by another spreading ridge, the Juan de Fuca Ridge. It is smaller and slower than the East Pacific rise. It spreads at about 6 centimeters a year. It has no continuous fame in the headlines, but it is the place to which a great deal of modern deep-sea biology and chemistry now goes to do its work. On the northern Endeavour segment of the Juan de Fuca Ridge, 2,250 meters below the surface, there is a vent field. It is called the Main Endeavour Field. It is about 260 kilometers southwest of Vancouver Island. It was first dredged in 1982 when a survey ship pulled up samples of metallic sulfide covered in small tube worms, and then properly visited in August 1984 when the deep submergence vehicle Alvin descended on leg 10 of cruise AII-112 and saw the vent field active for the first time. The field is not a single chimney, it is a forest of them. Along about 15 kilometers of the ridge, scientists have catalogued more than 800 individual chimneys, distributed across 6 major vent fields. The fields have names: Main Endeavour, High Rise, Mothra, Salty Dog, Sasquatch, and Stockwork. Within the Main Endeavour field alone, 16 distinct active venting sites have been named: Bastille, Crypto, Dante, Dudley, Easter Island, Grotto, Hulk, Lobo, Millie Q, Peanut, Puffer, Salou, Smoke and Mirrors, Sully, TP, Quebec. Each site is a clutch of chimneys. Each chimney a stack of mineral structures grown out of the seafloor by the slow precipitation of dissolved metals when superheated vent water meets cold, deep seawater. A single Main Endeavour chimney has been measured at 360 degrees Celsius at its mouth. The field has been active for at least 2,300 years. Some chimneys are alive, venting, growing, hosting communities. Others are dead, quiet now, scalable, mineral cold. The two stand in the same field. Active and inactive structures share the floor. Let us look at a single chimney closely. It rises from the basalt of the sea floor. Imagine a stack of dark mineral material growing not as a smooth cone, but as a craggy, uneven tower, narrow at the base, wider near the middle, sometimes pinched at the top. It is 20 meters tall. Some at Endeavour are taller. The largest chimneys recorded in the Pacific have reached 40 or 50 meters, the size of a 15-story building. One famous tower near Oregon, called Godzilla, rose to about 40 meters before it fell over in 1996. The chimneys can grow extraordinarily quickly. Vent growths on the order of 30 centimeters a day have been recorded. A chimney can add the height of a child every week, if its breath holds. The outside of the chimney is dark, encrusted, layered with sulfide minerals, pyrite, chalcopyrite, wurtzite, marcasite. Copper and iron and zinc all locked together with sulfur. The inside is hollow. Through the inside, hot water rises fast. At the top, where it meets the cold seawater, it bursts into a dark cloud. From a distance, the cloud looks like black smoke. It is not smoke. There is no fire here. There is no air. There is no combustion. It is a chemical cloud, a sudden precipitation of tiny mineral particles as the hot, iron-rich water collides with the cold, sulfide-bearing seawater and forms minute, dark grains of metal sulfide that hang in the water like soot. The whole structure is called a black smoker. The first black smoker ever seen by human eyes was found in 1979 on the East Pacific Rise by scientists from the Scripps Institution of Oceanography during the RISE project. They saw it from inside the deep submergence vehicle Alvin. They could not believe what they were seeing. They had expected fluids in the range of a few tens of degrees. The temperature gauge on the submersible's probe reached up past 350 degrees Celsius, melted, and reported nonsense. Later, more careful measurements showed that some black smoker vent fluids can exceed 400 degrees Celsius. The highest reliable measurement, at a site called Sister Peak in the Atlantic, is around 464 degrees Celsius. The water does not boil because the pressure of 3 or 4 kilometers of seawater above keeps it liquid, but it is, by every reasonable use of the word, superheated. The ambient water around such a chimney is about 2 degrees Celsius. The fluid coming out of the chimney is about 400. That gradient, almost 400 degrees across a distance of a few centimeters, is one of the steepest temperature gradients on Earth, and it is the engine of an entire ecosystem we will visit next. For now, just look at the chimney. Known black smokers across the Atlantic and Pacific have an average depth of about 2,100 meters below sea level. They sit almost always near divergent plate boundaries or at intra-plate volcanic centers, places where the planet's heat is close enough to the sea floor to drive a hydrothermal system. The deepest known black smokers are at a vent field called Beebe in the Cayman Trough in the Caribbean, about 5,000 meters below the ocean's surface. The most northerly known black smokers are at a vent field called Loki's Castle on the mid-Atlantic ridge between Greenland and Norway at 73 degrees north. A cluster of 5 chimneys discovered only in 2008. There are also white smokers. Their plumes are pale rather than dark. They carry barium, calcium, and silicon rather than iron sulfides. They tend to be cooler than black smokers, and are usually further from the central heat source. Black and white smokers often share the same hydrothermal field. They're the close and distant cousins of the same underlying chemistry. Where the magma is hottest and closest, the smoker is black. Where the heat has cooled and the fluid has had more time to mix with seawater, the smoker is white. The chemistry of the inside of a chimney is, if you do not mind a moment of patient detail, worth a moment of attention. Cold seawater filters down through cracks in the basalt, sometimes for kilometers, until it reaches rock hot enough to react with it. There, the water loses its magnesium and its sulfate. It picks up calcium and potassium and silica from the rock around it. Where it touches the hottest, deepest, freshest basalt, it strips out iron and copper and zinc, small amounts, but multiplied across decades and centuries, enough to build a tower. By the time the water has finished its journey through the crust and begun its rise back to the sea floor, it is unrecognizable. It is hot. It is acidic. It is reduced rather than oxidizing. It carries hydrogen sulfide and dissolved metals in concentrations the surface ocean would find chemically violent. It is, in chemical terms, almost the opposite of seawater.
Then it meets the cold. The metals precipitate out almost instantly. The dark cloud forms. The tower grows another fraction of a millimeter. The cycle repeats. It has been repeating, in some places, for thousands of years. At Endeavour, the chemistry of the field has changed more than once in living memory. In 1999, a diking event, a sudden injection of magma into a crack in the crust, was detected by the United States Navy's SOSUS hydrophone array. The vent geochemistry shifted across the entire field. Another diking event was detected in 2005.
After these events, the hydrothermal activity at main Endeavour has been slowly waning. Some sites, like Milicu, have gone extinct. Some chimneys have begun to cool. New ones have started up elsewhere. The field is alive in the way a long, slow forest is alive. Individual trees come and go, but the forest persists for a while. The field is also, as of 1993, a Canadian marine protected area covering about 97 square kilometers of ocean floor. It was the first deep-sea hydrothermal system in Canadian waters to be granted formal protection. The protected zone covers 6 major vent fields and the surrounding ridge axis. No fishing, no mining, only research. The chimneys are left to breathe. Move a little south. Now, along the Juan de Fuca Ridge, about 480 kilometers west of Cannon Beach, Oregon. The seafloor here lifts into a small underwater shield volcano called Axial Seamount. It stands 1,100 meters tall, with its summit at 1,410 meters below sea level. Axial is unusual. It sits at the intersection of a hotspot and a mid-ocean ridge. It is one of the most heavily instrumented seamounts on Earth. It was the first submarine volcano whose eruption was detected and tracked in real time in January 1998. Subsequent eruptions in April 2011 and April 2015 were also caught. Volcanologists working with seafloor strain meters and pressure gauges have publicly forecast a likely next eruption around the year 2026. The seafloor itself, in this small place, is now being watched the way meteorologists watch a hurricane. Think about that for a moment. We have built on a quiet ridge 2.5 kilometers below the Pacific surface, off the coast of Oregon, a long-term observatory that tells us when the floor of the ocean is about to breathe out. Not perfectly, not exactly, but better than chance. This is, in its quiet way, a small triumph of patient human attention. Now let the field around us settle. Picture the Endeavour Ridge in our imagination one more time. 800 chimneys, more or less, scattered across 15 kilometers of basalt. A handful actively venting, dark plumes curling up into the cold water and rising perhaps several hundred meters before they reach what is called the neutrally buoyant level, the depth at which their dissolved load is just dense enough to stop rising. From there, the plumes spread laterally, sometimes for thousands of kilometers, dispersing iron and helium-3 and other traces across whole ocean basins. The vents are not local features. Their breath touches the entire Pacific. Around each active chimney, in the warmer water at the base, something else lives. Something that does not need sunlight at all. Something that has built a garden out of poison. Sit with us a moment, in the warm dark, among the gardens that drink the Earth's heat. The gardens that drink the Earth's heat grow in absolute night. There is no sunlight here. There has never been sunlight here. The chemistry that supports them is older and stranger and, in a quiet way, more universal than the chemistry that supports the green forests on land. Move with us closer to the base of a chimney. The plume rises from its mouth, black against the dark, but the water at the bottom of the chimney is warmer than the surrounding sea. Not scalding, just warm. 40 degrees Celsius in some places, 30 in others. 2 degrees, the ambient deep, a few meters away. The transition zone, where the plume has cooled to body temperature, is where life lives. And life lives. In the warmer water around the chimney, on the basalt itself, on the cooling outer walls of the tower, in every crevice, a thick white mat of bacteria. Not green, not the color of leaves, pale, almost translucent. The mat is alive. It is feeding. It is not feeding on sunlight, because there is no sunlight to feed on. It is feeding on the dissolved chemicals in the vent water itself. Hydrogen sulfide mostly, methane sometimes, hydrogen sometimes, iron, manganese. The bacteria oxidize these compounds the way the bacteria of the surface world oxidize sugar, and they convert the released energy into organic matter. Carbon dioxide dissolved in seawater is their carbon source. Sulfide is their fuel. They are, in the formal biological term, chemosynthetic. They build life out of chemistry alone. This process is called chemosynthesis. It was identified in this context in the early 1980s by a young microbiologist named Colleen Cavanaugh, working out the symbiosis at the heart of a creature we are about to meet. Chemosynthesis is what the chemoautotrophs do. Sulfur-oxidizing gamma proteobacteria, methanogenic archaea, neutrophilic iron-oxidizing bacteria, and a small handful of other lineages. They use the oxidation of inorganic compounds, rather than sunlight, as a source of energy. They have probably been doing this for the entire history of life. Some of the deepest branches of the tree of life are chemosynthetic. There is a real possibility that life itself began in conditions like these, near vents on a young Earth, before photosynthesis had been invented. The mat of bacteria is the floor of the garden. Above it grow the larger things. There are sometimes clusters of pale clams as big as a flat hand. Calyptogena magnifica is the species name, sitting half buried in the basalt, taking warm water in and filtering it. There are pale mussels, Bathymodiolus thermophilus, clinging to crevices. There are eyeless white shrimp, sometimes in such numbers that the rocks look like they are crawling. There are crabs, octopuses, polychaete worms. There are small fish that have evolved nowhere but here. Over 300 new species have been described from hydrothermal vent communities since the first vent dive in 1977. Many of them are sister species to each other, separated by long stretches of cold, deep ocean where vent life cannot easily cross. They're like the finches of separate islands, only the islands are smoking chimneys, and the cold sea between them is a stretched-out continent. And in the middle of all this, sometimes in such density that the rocks look upholstered, grow the tube worms. They are the signature creatures of the Pacific vent fields. Their species name is Riftia pachyptilla. Their common name is the giant tube worm. They were discovered, along with the first vent garden, in 1977 during an expedition led by the geologist Jack Corliss to the Galapagos Rift. The dive was sponsored by the Woods Hole Oceanographic Institution and the National Science Foundation. The submersible used was the American bathyscaphe DSV Alvin. The presence of thermal springs near mid-ocean ridges had been theoretically predicted. The team was sent down to confirm them. The team had no biologist on board because the vents were assumed to be sterile, too hot, too toxic, too far from sunlight to host anything alive. What they saw instead was a forest. The first such site they reached, dubbed the Rose Garden because of the prevalence of red Riftia tubes, was crowded with creatures. White crabs, foot-long clams, beard-like worms standing upright on the basalt, their tops crowned with bright red plumes. One of the geologists on the expedition, looking through the viewport of Alvin, compared the discovery to Columbus reaching the Americas. They were looking, in a real sense, at a continent of life no one had known existed. Let us look at one of those red-plumed worms. It is a long, pale tube, 3 meters tall in the largest specimens, a little more than 4 centimeters across. The tube is made of chitin and protein. It is anchored at the base. The top of the tube is open, and through the open top, a soft cylindrical body extends upward, ending in a feathery, bright red plume. The plume is what you see first. It looks like a flower. It is the color of arterial blood. If you brushed your hand near it, if you were down here and could, the worm would retract the plume instantly into the tube and seal the opening with a small lid called the obturaculum. The garden would close, briefly, around you. This is what is strange about the worm. It has no mouth. It has no digestive tract. It has no anus. It cannot eat. It cannot, in the conventional sense, feed. And yet, somehow, the largest individuals are 3 meters long. How? The answer is that the worm is not, by itself, a single organism. It is a partnership. Inside its body, in a soft, spongy organ called the trophosome, lives a population of chemosynthetic bacteria, roughly 1 billion of them per gram of tissue. They are the worm's lungs, gut, and farm at once. The worm grows the bacteria. The bacteria feed the worm. The bright red plume is a transport system. It is full of a specialized hemoglobin, up to 144 globin chains in a single molecule, far more than the simple 4-chain hemoglobin in our own blood. This vent hemoglobin can do something ours cannot. It can carry oxygen and hydrogen sulfide at the same time, without being poisoned by the sulfide. The hemoglobin scoops both molecules out of the surrounding water, the oxygen from the cold seawater, the hydrogen sulfide from the warm vent plume, and ferries them down through the body into the trophosome, into the bacteria. The bacteria use the hydrogen sulfide as fuel. They use the oxygen as the burner. They convert dissolved carbon dioxide into organic matter. The worm absorbs what it needs from them. That is the entire arrangement. No food chain, no sunlight, no photosynthesis. Just a worm and a bacterium and the breath of a chimney. There are other creatures that have learned to live this close to the planet's heat. The Pompeii worm, Alvinella pompeiana, makes its tube directly on the walls of black smoker chimneys, in water hot enough to denature most proteins. It survives temperatures up to around 80 degrees Celsius, possibly the highest tolerated by any animal known. The scaly-foot gastropod, Chrysomelon squamiferum, found in 2001 at a vent field in the Indian Ocean, builds the protective scales on its foot out of iron sulfide minerals rather than calcium carbonate, making it the only known animal whose armor is, in part, magnetic. There are eels at Waialulu'u called Eel City. There are limpets and amphipods and copepods in every crevice. There is even, far away on the mid-Atlantic ridge, a species of bacterium that uses the faint glow of a black smoker, not sunlight, but the dim infrared glow of 200-degree water against cold sea for photosynthesis. The only photosynthesizer known to nature that uses a light other than the sun. Let that sit. Photosynthesis without the sun. A real organism, found in nature, quietly, in the dark. Now think about the Rose Garden again, the original site at the Galapagos Rift. A return expedition in 1985 found that the worms there were fewer in number, displaced by clams and mussels, even though the water chemistry was essentially the same as it had been in 1977. Vent communities shift like that. The chimneys cool, or change, or get covered by lava. The species that thrive change with them. A return expedition in 2002 found that the original rose garden had been destroyed by a lava flow sometime in the prior decade. The garden was gone. The worms were gone. The clams were gone. The basalt that had once held them was buried by fresh basalt. But a few hundred meters away, the team found a new community. The worms were back. Younger, smaller, but back. They named the new site Rosebud. The garden does not have a fixed address, it has a strategy. When a vent dies, the larvae of vent species, tiny, drifting, almost invisible, disperse with the currents, looking for new warm water. Most die. A few find another vent somewhere along the ridge. A few survive. A new garden begins. The chimneys outlast the worms. The worms outlast the chimneys. The Pacific is a slow circulation of warm pulses and cold dark, and the gardens move between them, persistent without being permanent. Sit a moment in the warm dark. Around you, soft pale tube worms. Above you, the dark plume of a chimney. Below you, basalt. Around you, billions of bacteria you cannot see, breathing sulfide in absolute night. They have been doing this for as long as there have been continents, probably much longer.
Now turn west. The sea floor on which all of this sits is not stationary. The plate is moving. Where it is going, eventually, is the only other question worth asking. Where does all this go? It goes into the trenches. It goes west across the floor of the ocean and falls. Drift with us, west, across the trench arcs.
It goes into the trenches, the new ocean floor born at the ridges, the basalt of every chimney, every tube-worm garden, every quiet, sediment-covered plain. All of it is moving, slowly, in one direction or another, toward a place where the sea floor folds down and disappears. The Pacific is a moving plate. Its eastern edge is being built at the rises we have visited. Its western edge is being eaten at the trenches we are going to visit now. We drift west, then across the center of the Pacific, across the sea floor that is, by now, 100 million years old. The basalt below us has been quietly drifting since before the dinosaurs went extinct. Plankton has snowed down on it for tens of millions of years. The sediment cover here is thick and pale, in places hundreds of meters deep. The sea floor is older, cooler, heavier. It rides lower in the mantle than the new floor of the rise, and it is heading, slowly, toward a long, arcing wound in the western Pacific that no one knew existed for most of human history.
The wound is called the Mariana Trench.
It lies about 200 kilometers east of the Mariana Islands. It is the deepest oceanic trench on Earth. Crescent-shaped, 2,550 kilometers long, 69 kilometers wide. At its deepest point, a small slot-shaped valley called Challenger Deep, the seafloor reaches 10,984 meters below sea level, give or take 25 meters of measurement uncertainty. That is more than 2 kilometers farther from sea level than the peak of Mount Everest is above it.
If you could pick up Everest, summit and base together, and drop the whole mountain into Challenger Deep, the peak would still be more than 2 kilometers underwater. The water at the bottom of the trench presses down with about 1,086 bar of pressure, roughly 1,071 times the standard atmospheric pressure at the surface. 8
tons on every square inch. The water temperature there is between 1 and 4 degrees Celsius. And there is life. Single-celled organisms called monothalamia have been retrieved from depths around 10,600 meters, almost at the floor of the trench, by researchers from the Scripps Institution of Oceanography. Below that, in the sediment itself, more microbial life. Down there, in a place where the pressure would crush any submersible not specifically built for it, things still live. The trench is what happens when the floor of the ocean meets the edge of another plate and is forced down. Here, in the western Pacific, the long-cooled, heavy Pacific plate slides beneath the lighter, smaller Philippine plate at a low angle, vanishing into the mantle below. The sea floor that began its life at the East Pacific Rise 80 or 100 million years ago is now, here, returning. The trench is the doorway. The plate goes down through it into the deep earth and is reabsorbed. This process, the descent of one plate beneath another, is called subduction. And subduction does not happen quietly. As the cold, wet plate sinks, it releases water into the mantle above it. The water lowers the melting point of the rock around it. New magma forms. The magma rises. Some of it reaches the surface, building a long, curved chain of volcanoes above the descending plate. That chain is called a volcanic arc. The Mariana arc is one. The Tonga-Kermadec arc, far to the south, is another. The Aleutian arc is another. The Pacific is rimmed with them. They are called, collectively and unofficially, the Ring of Fire. The Mariana Arc is one of the busiest of these. It stretches about 2,500 kilometers along the line of the Izu-Bonin-Mariana volcanic arc and contains between 52 and 60 submarine volcanoes, about 5 times as many as rise above sea level. At least 20 of those submarine volcanoes are hydrothermally active. Most of them have only been identified in the last few decades. One of them is the volcano we have come this far to see. Its name is NW Rota 1. It lies about 64 kilometers northwest of the island of Rota in the Commonwealth of the Northern Mariana Islands, and about 100 kilometers north of Guam. Its summit is 517 meters below sea level, shallow enough that the water above it is in the twilight zone. The volcano is a steep cone, rising from a base 16 kilometers wide at depths of 2,700 to 2,800 meters up to that 500-meter summit. It was discovered to be hydrothermally active by the United States National Oceanic and Atmospheric Administration in 2003. In 2004, NW Rota 1 became the first volcano on which a submarine explosive eruption was directly observed. This is, in the long history of human volcanology, a small miracle. Almost everything we know about explosive volcanoes had come, before this, from above-water examples. Vesuvius, Mount St. Helens, Pinatubo. We had never sat at the foot of a vigorously exploding submarine volcano and watched it work. Remotely operated vehicles, small unmanned submersibles, were sent down to northwest Rota 1. They held position near the summit. They watched. What they watched was a small, steep crater near the summit called Brimstone Pit, sending up strombolian bursts. Imagine a series of low coughs from the sea floor, gas-rich magma rising through the throat of the volcano, releasing in pulses, throwing up clots of glowing lava and clouds of dark tephra into the water above the crater. The plumes were rich in droplets of molten sulfur, which gave the crater its name. The eruption did not look like an explosion on land. Underwater, the pressure of 1/2 kilometer of seawater above the crater rim damped everything. The eruptions were slow, they were stately, they were almost gentle to watch. Watching them, marine scientists realized that NW-Rota-1 was releasing carbon dioxide on a measurable scale, about 400,000 tons per year, give or take 100,000 tons. Most of it dissolves into the deep seawater immediately above the vent. Bubbles of carbon dioxide can be seen in still images rising from the crater. The seawater at the summit is more acidic than the average ocean. The bubbles are part of a continuous, very slow exchange. The planet exhaling its inner carbon back into the sea through this one small, steep cone in the Mariana Arc. The whole volcano is unstable. Its slopes are covered in volcanic debris, sulfur globules, scree, broken pillow lavas. Material accumulates around the active vent until the slope gives way. Landslides are common. The most recent large one occurred on the 14th of August 2009. A piece of the southern flank slid downhill with an estimated volume of about 1/2 cubic kilometer. The displaced rock and sediment generated a plume of ash-rich water that spread several kilometers from the volcano. It did not, however, generate any detectable tsunami at the surface. The eruption is muffled by the deep. The world above did not notice. There are other arcs. There are other quietly erupting submarine cones. Far to the south, on the Tonga Kermadec Ridge in the southwest Pacific, lies Havre Seamount. In July 2012, it erupted, silently, deep below the surface, and produced one of the largest deep-sea silicic eruptions ever observed by modern science. The first hint of it was a vast raft of floating pumice spotted by an airline pilot, riding the ocean surface for hundreds of kilometers downwind. Below the surface, the eruption had emplaced lava domes, ash beds, and a thick blanket of fresh pumice across the summit area. The plume of pumice could be seen from space. The eruption itself was never seen by any human eye. Somewhere in the trench arcs of the Western Pacific, something like this is happening right now. We just are not looking at it. Think for a moment about the geometry of all this. The Pacific plate is sliding into the mantle at a low angle. Down it goes, first a few degrees from horizontal, then steeper, until at depth it is descending at perhaps 40 or 50 degrees into the deep earth. The chemistry of the descending slab changes as it sinks. The water it carries is squeezed out into the rock above. The rock above melts. The molten material rises through the wedge of mantle between the descending plate and the overriding plate. Some of it pools. Some of it reaches the sea floor. Some of it builds the Mariana cones. Some of it, at End-West-Rota-1 specifically, builds magma that is among the most water-rich in the entire Mariana Arc. The cycle that began with seawater seeping into a crack in the East Pacific Rise basalt thousands of kilometers away and 100 million years ago ends at the Brimstone Pit, with carbon dioxide bubbling slowly into the warm, dark water above the crater. The same water, the same atoms, just enormously older.
Nothing is wasted. Nothing is added. Nothing is removed. The Earth is a closed loop with a very slow clock. Sit for a moment on the inner slope of the Mariana Arc. The volcano below you is venting carbon dioxide slowly into the water. The plate to your east, the sea floor we have traveled across, the basalt that was once new at the East Pacific Rise, the basalt that once carried the chimneys of Endeavour, is sliding beneath you, going down into the trench, returning to the mantle. The chimneys it carried are gone. The tube worm gardens it hosted are buried under sediment somewhere west of here, or they have been pulled below the trench rim and lost. Nothing of what we have visited will be permanent. The plate that birthed it will eventually eat it. It is not a death. It is not a wound. It is not an end. It is the other half of a long, slow breath. We are nearly done. There is one place left to rest: the slow cycle of the sea floor. Not a death, not a wound, not an end. The long cycle of the sea floor is older than any of the words we have for endings. It is the slow inhale at the rise, the slow drift across the basin, the slow exhale at the trench. It has been turning over for as long as Earth has had oceans, in some form. It is what makes the planet you live on. And it does not stop. Ever. Sit with us a moment, in the dark water, while the cycle turns. The basalt of the seafloor under us, the basalt we have crossed for the last hour, was made at a rise like the East Pacific Rise, at some time and place we cannot now point to, by the same patient process. It cooled in the cold seawater. It became part of a moving plate. It drifted away from where it was born, slowly, at the speed of fingernail growth. Sediment settled on it in long, quiet snow. Vents grew on it and died on it. Tube worm gardens flourished on it and were buried by lava. Volcanoes rose on it and were dragged toward trenches. Eventually, in 50, 80, 150 million years, it reached an edge. It bent down. It went into the mantle. The atoms in it were melted, mixed, redistributed. Some of them, decades or millions of years later, came back up at an arc volcano somewhere else. Some of them came back up at a hotspot. Some of them are still down there. The cycle does not care about any one piece of rock. The vent gardens we have visited do something similar. A single chimney is not very old. A few decades, a few centuries, perhaps a couple of millennia for the longest lived. The main Endeavour field has been venting for at least 2,300 years. Some chimneys persist that long, many do not. A volcano in the Mariana Arc may last for tens of thousands of years. Many do not. The gardens move from chimney to chimney, from vent to vent, from arc to arc. Their larvae drift in the cold dark, looking for warmth. Most die. A few find it. Vent life is patient. Vent life is also fragile. The animals that live there are perfectly adapted to a habitat that is, on geological timescales, a flicker. They have learned to use the flicker. This pattern, chemistry plus heat plus liquid water in the absence of sunlight, supporting life, is not unique to Earth. The Lost City hydrothermal field on the mid-Atlantic ridge in the Atlantic Ocean has been alive for at least 30,000 years. It is a different kind of vent system from the Pacific black smokers. Its water is cooler. Its chemistry is alkaline, not acidic. Its energy comes not from magma, but from a slow chemical reaction called serpentinization, in which seawater reacts with deep mantle rock and abiotically produces simple molecules, hydrogen and methane and others. Lost City is considered today a prime analogue for the conditions in which life on Earth may have begun. Vents like it 4 billion years ago may have been the first cradles. Some of the oldest branches of the Tree of Life trace back to chemistry like lost cities. And if it can happen here, it can happen elsewhere. Active hydrothermal vents are now believed to exist beneath the ice shell of Jupiter's moon Europa, 2.5 billion kilometers from the Sun. The icy crust above them is many kilometers thick. The ocean below them is liquid, kept warm by tidal flexing as Europa orbits Jupiter. Saturn's small moon Enceladus is the same, a thin ice shell over a global subsurface ocean, and jets of water vapor erupting from cracks at the South Pole. Cassini, the spacecraft that flew through those plumes in the early 21st century, found evidence of hydrothermal activity on Enceladus's seafloor. Methane, hydrogen, silica, the signatures of vents like the ones we have just visited. There may even, it is speculated, have been hydrothermal vents on ancient Mars, billions of years ago, when Mars still had liquid water beneath its surface. If there is life on any of those worlds, it almost certainly does not look like ours. It almost certainly lives in the dark. And it almost certainly drinks the chemistry of vents like the ones at Endeavour and Loihi and the Mariana Arc. So when we say that the vent gardens of the Pacific are universal, we mean it in a quiet, literal sense. The pattern is the planets, but it is also potentially the solar systems. The same kind of warm, dark chemistry happens, perhaps, beneath ice shells very far away. The tube worms here have, perhaps, distant cousins out there. Cousins we will not meet in any of our lifetimes. Cousins we may never meet at all, but the chemistry says yes. Let that thought settle in, quietly. We're going to leave the Pacific now. We're going to leave the chimneys at Endeavour, the tube worm gardens, the steep crater of NW Rota 1, the long, slow spine of the East Pacific Rise, the trail of the Hotspot, the rising shoulder of Kamaʻehuakanaloa. They will keep doing what they were doing before we arrived. The Pacific Plate will keep drifting northwest at 10 centimeters a year. Magma will keep rising under Hawaiʻi. Chimneys will keep growing and falling. Tube worms will keep being born and being lost.
Carbon dioxide will keep bubbling slowly out of brimstone pit. The trench will keep eating the floor of the ocean. None of it will pause for us. None of it ever has. But as you drift towards sleep, maybe you can imagine it. The warm, dark water at the base of a single chimney somewhere off the coast of British Columbia, with the pale tube worms standing on the basalt and the slow, steady plume of black mineral cloud rising into the cold above them. The whole field humming, gently, at the very low pitch of the planet's interior. The whole Pacific around it, vast and dark and quiet. The continents far above, with their cities and their forests, going on with their fast lives in their thin film of air. The two worlds, your world above and the long, slow workshop below, turning together on the same axis, breathing the same slow breath, neither one knowing the other very well. Two worlds, two timelines, the same night falling over both of them. The deep cycle does not care whether you watch it or not. It has been turning for billions of years. It will keep turning long after we are done. But for an hour, you watched it. For an hour, you sat in the warm dark with the gardens and the chimneys and the slow, patient breath of the planet. That is, in its quiet way, a kind of communion, a kind of knowing. Let your breath slow. Let the lamps of the world above dim a little further. The plate below you is moving. The chimneys below you are venting. The tube worms below you are drinking the sulfide of the Earth's heat. The trench is doing what trenches do. Nothing is wasted, nothing is added, nothing is removed. The Earth is breathing, slowly, in the dark. Close your eyes if you have not closed them already. The sea down there is the same temperature whether you watch or not. The chimneys do not need to be seen to keep growing. The tube worms do not need to be heard. They are doing what they have done since long before you were born, and they will do it after. You are very small. The sea is very large. The cycle is very slow. And in that smallness, in that largeness, in that slowness, there is, if you let it, a very deep peace. Sleep well, child of the slow Pacific furnace. Good night.